Alright, so last we got part 3 here. An article in USA Today says basically directory assistance providers give out the wrong number 12% of the time. Assume you're testing such a provider, making 50 phone number requests. Assume the provider gives the wrong number 12% of the time. So this is going to be a binomial distribution. And we know that because what we're talking about has two possible outcomes, a wrong number or a right number given. And we've got n is the number of trials, which is the 50 numbers that we're requesting. Let's say the probability of getting it wrong is 0.12. Probability of getting one right is 1 minus that, or 0.88. So those are our parameters for this binomial experiment. Now, what we're asked is, first, of the 50 requests, on how many would you expect to be given a wrong number? Well, this is somewhat straightforward. And we'll say, for part A, the expected number of wrong numbers in a binomial experiment, that's n times p, or 50 times 0.12, which equals 6. So basically speaking, if you expect 12% of them to be wrong and you ask for 50 numbers, you'd expect 12% of them to be wrong. 12% of 50 is 0.12 times 50, which equals 6. So there's part A. Part B asks, what's the probability of getting exactly one wrong number? So here we're going to use the binomial probability formula. And let's just put that up here. Probability, the random variable has a value of x, or in this case, probability of getting a particular number of wrong answers is going to be n factorial over n minus x factorial times x factorial, where n is the number of trials, which is 50, x is the number of wrong numbers, times probability of a wrong number to the power of x, which is how many wrong numbers, times q, the probability of a correct number, to the exponent of n minus x, or how many. So probability of a wrong number, how many wrong numbers, probability of a correct number, how many correct numbers. So the probability of one wrong is going to be 50 factorial over 50 minus 1 factorial times x factorial times probability of a wrong number, how many, probability of correct number, how many, and that probability is going to be, and we can calculate that on our calculator. We'll get 50 factorial divided by, and we'll do parentheses because there's two things on the bottom, 49 factorial times 1 factorial times p to the 1 times 0.88 to the 49th. That equals 0.0114. So 0.0114 or 1.14%. So probability of getting exactly one wrong number out of 50 is 1.14%. Part C asks, what's the probability of getting at most one wrong number? So here we've got an event, so probability of at most one wrong. It's a compound event, so it's the probability of getting none wrong plus the probability of getting one wrong. So at most 1 means less than or equal to 1, which means 0 or 1. So the probability of getting none wrong would be the probability of getting all right plus the probability of 1 wrong. And that's going to equal, the probability of all right is 0.88 to the 50. So basically the probability of getting the first one right is 0.88, the second one 0.88, the third one 0.88, etc., etc., etc. Since they're all independent events, you don't assume that getting a number right or wrong is dependent on the call before or the call after. So the string of 50 wrong or correct numbers, correct numbers, 0.88 times 0.88 times 0.88, etc., 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 50 times. So that's the probability of all of them correct or none wrong. And then we know the probability of getting one wrong is 0.114. So that's going to give us .0017 plus 0.0114. That equals 0.0131 or 1.31%. So the chances of getting at most one wrong are 1.3%. Now for Part D. Part D says, based on the findings above, if you got at most one wrong number out of 50, does it appear that the rate of wrong numbers is actually 12%? So what this does is get back to what we've been talking about with assumptions and probability. So we make an assumption. So our assumption is 12% is the rate of wrong numbers given. Based on this assumption, what can we say about the probability of getting at most one wrong? So based on this assumption, the probability of getting at most one wrong is 1.31%. This, we would say, is unusual. And what we've said is, we make an assumption. If the probability of something happening based on that assumption is small, or if it's unusual, maybe our assumption isn't a good one. So based on this is unusual to get so few wrong numbers. We expect 6, we got no more than 1. Maybe this isn't a good assumption. Okay, so maybe to get that few, maybe the rate's lower. So what happens if the rate, let's say just for kicks, does 7% seem like a reasonable rate? What's the probability of getting at most 1 wrong if the rate is 7%? Well, the probability of 0 or 1 wrong out of 50 would be, probability of getting 0 wrong would be all correct, but now we've got a new P and Q. P would be probability of getting 1 wrong is 7%. The probability of getting 1 right is 93%. So all right would be this. Probability of getting 1 wrong would be 50 factorial, 49 factorial, 1 factorial, P to the 1, and Q to the 49. And that, after I do all my algebra, 0.1265, 12.65%. So, assuming a lower rate, getting 1 or none wrong, at most 1 wrong, isn't so unusual. So maybe, in fact, the rate of 12% isn't correct. Maybe the rate is actually lower, which is why we got so few wrong in our sample of 50. Is it 7%? Is it 8%? Is it 9%? Who knows? But it doesn't seem that 12% is accurate. Okay, the real rate isn't 1.3%. That's just the probability of getting at most 1 wrong out of 50, assuming a 12% incorrect rate. But since it's an unusual event, it appears as if maybe, in fact, the rate of wrong numbers is lower.